So, good afternoon, ladies and gentlemen. This is the last crash course, the last of the 3-day Hadoop session, 3 days. It's been a very long one, and I think it's been long for everybody. I welcome all of those of you who came back for another session, another repeat. Again, we'll try to keep it to about 45 minutes, about an hour lecture, and then about an hour for the lab. So I'll go over the lab, and then if you have any issues, we'll step into to help you out, run some things, and then I'll go over the lab again, step by step, with all the details. So again, the plan is to quickly go through some of the big data background, cover the Spark core or the resilient distributed datasets or RDDs, cover Spark SQL and data frames, briefly what Spark streaming is, the Zeppelin notebook that you'll be using in your environment, in your sandbox, and then a little bit more on what the sandbox actually is, and of course the lab preview. So let's go, you've been hearing this of all the different keynotes, all this big data, but again, all these edge nodes, all these sensors, whether it's oil rigs or wind farms, they're producing lots and lots of data. So we need the tools to process all this data and make meaning of it. And the data grows very rapidly. Some estimates say that by 2020, there will be 65 zettabytes of data, and 1 zettabyte is 1 million terabytes. So there's quite a bit, especially if you compare that all of Wikipedia with all the text, with all the thumbnails, is only 128 gigabytes. And nowadays, you can fit all that data onto one USB stick. So the data is growing quickly, the data is growing exponentially. Hadoop is one of the platforms that you can process on, and Spark is an excellent engine if you want to do a lot of these things, a lot of these processing in memory. So let's just go back and what is the big data problem in general? So everything started that one machine could not process everything. We needed a distributed way of processing data across different servers or nodes. That's where the concept of clusters came in. What was the difficulty? Well, how would you split the work across the machines? How would you move the data across the network, knowing that the data is expensive? How do you minimize that movement? Things to consider like data and network locality. How do you deal with failures, right? That's a difficult one. How do you recover from failures? And how do you deal with slow nodes? So we'll try to address some of these things and how Spark comes in to address them and work with that automatically. So a little Spark background. All of you probably know that memory in general is very fast. I had some numbers before, but these numbers do seem to be switching quite rapidly. So the memory is faster, the hard drives are getting faster, there's a lot of caching in between. But generally the concept is that between the servers, between the servers themselves, there's the slow network connection. The hard drives are much slower than the RAM, and pulling data from the hard drives to RAM is slower than just pulling all the data from RAM into the CPU. So the more data you have in memory, the better performance you will get out of Spark. And that's the whole concept of Spark, is this phenomenal in-memory system, in-memory engine. Going a little bit about this classic map reducer going back to 2004, also on a very high level, every iteration, every step, every process you take, it would reading from the hard drive, and then after one iteration, you'd be writing the intermediate results back to the hard drive, and so on and so forth. And that was slow, writing and reading from the hard drive. So the concept was like, well, what if we pull on this data to memory, do all the iterations in memory, all the different steps, and then grab the results. And then we can either visualize the results, on some kind of dashboard, or we save the results to the hard drive once we're done with the iteration. So when you go with bigger memory systems, it definitely performs a lot better. Of course, this is already available. Back in last year, it was announced that this 2 terabyte memory X1 Instant on Amazon, this was, at the time, it was an order of magnitude faster, about 5 times faster than what Microsoft offered, and all these companies such as SAP HANA, Microsoft, they realized that having more memory to work with, to have this data locality is very important. So what is Spark? Well, it's an open source project initially developed by AmpLab in Berkeley. It's a data processing engine. It's an in-memory distributed computing. And it's got a very rich set of APIs. And the APIs are useful for whether you're programming Scala, Python, R, or Java. These are the core components of Spark. The first layer is the Spark core. That's where RDDs reside. This is the first layer that's been built. And on top of that, you have several different modules. You have Spark SQL, streaming, machine learning, and GraphX for graphical analysis. And we'll cover those in detail. So why Spark? Why people care about it? Well, it's got an elegant set of APIs. It's a single environment for data munging or data cleansing. It's phenomenal for machine learning, distributed machine learning. It's got that, again, in-memory computational model, which is fast. And implementing machine learning models, especially with the Spark ML, this pipeline machine learning models, is efficient and fast. Here's a brief history. As you can see, Spark is only about 2 years old. And the whole big data with MapReduce, the initial paper was published only in 2002. Hadoop at Yahoo, 2006. The first summit, 2008. So this summit has been going on for quite some time. Let's go over some basics. So when you start, when you initialize Spark, you might be wondering, what is this SC, or Spark context? And this is essentially the main entry point to Spark. So anything that you will be doing with Spark, you will start with the Spark context. And for you, it's an easy way to get started. You just go SC something, bring in some of the data, and it's already parallelized. It's converted to RDD. Underneath, it's a connection to the cluster. It's the entry point to the cluster and managing cluster from that point on. So what are RDDs? I'm going to cover them briefly because they're the lower level, and we're going to focus on the higher level stuff. But it's important to understand because they will, every time you look at a Spark documentation, you will see, you will find a description of RDDs. And essentially, it's a primary abstraction in Spark. It's a collection of immutable objects, or objects that do not change, that are not overridable. You just transform them and write them into something, a new RDD, and they can be operated in parallel. They're distributed, which is the whole concept of parallelism. So you have elements partitioned across different nodes. You can control the number of partitions if you figure that you would like to have more or less partitions. Maybe you want to have 1 partition instead of 8 partitions, or vice versa. And they're resilient. So the whole concept is that they can themselves recover from node failures. So if your node does fail, it can recover on its own, which is a very important thing, especially in distributed systems. And if there's an RDD or a node that is slow, it will be able to spin up another node. And if that node finishes it before the slow node does, it will take the computations that have been taken on that node. And the whole concept of lineage, of going back historically and knowing where to start from if there was a failure, that's also a very important thing that was developed within the Spark engine itself. So also very, very high level, if you're bringing data from like a big data store such as HDFS, you would have certain block sizes. So if you're bringing the data, this is more of like a MapReduce flow, but it's very similar to what happens in Spark. If your data is partitioned and it's got different blocks, those blocks would represent the partitions automatically. Because some of you had questions like, so how are these partitions created? If you have a block size on HDFS, each block size would essentially correspond to a separate partition. And of course, you could repartition that if needed, or if you have not enough partitions because the data set is small, you could increase the number of partitions to have that parallelism in your code. So here's a good example of having 2 different RDDs. RDD1 having 4 partitions, RDD2 having 3 partitions. And as you can see, it automatically assigns where these RDDs or these specific partitions will be executed on these nodes. And again, these nodes will be your compute systems, whether it's your servers or even some local machines that connect. Anything that can compute, anything that got some kind of storage where it can access the data and pull in memory. So let's talk about Spark SQL. And the essence of Spark SQL is that if you're coming from the world where you've been writing SQL queries, you can access that world with Spark. So Spark SQL is a module for, as you've seen at the very, very beginning diagram, there's a Spark core and there's Spark SQL and a few others. So Spark SQL is one of those modules that's been designed for structured data processing. So you're looking at database tables, you're looking at JSON files, and it's very easy to manipulate a lot of that data. What comes within that Spark SQL module are 3 things. You can either manipulate data using the data frame API syntax, which we'll go over. You can write SQL queries. And that's essentially by exporting or creating a temporary file, temporary table from those data frames. And there's this latest new datasets API, which combines the best of all the worlds, which is, you got this data frames speed up, and you have this RDD low-level type of ability to compute data and have this Lambda architecture. We're not going to cover data sets in this session, but we're going to focus on the data frames and SQL queries because it's very easy to get into. And very importantly, regardless of which API you will use, and that's spelled out more deeply in the lab itself, they have the same execution engine underneath. So you have the same optimizations being performed by what's called the Catalyst Optimizer in Spark. I'll have a quick figure on that one as well. The benefit is that you provide additional information to the Spark SQL, and because it has the information about the structure, it can assign and find what's the best model and convert it back to RDDs, which of course are parallelizable and can be computed in a distributed manner. So data frames, this concept comes from the world of R or Python. They're conceptually equivalent to the data frame in those two languages. And they've developed this API, and it's accessible both in Scala, Java, Python, and R. And like I mentioned before, the core concept here is that they're significantly faster than RDDs because they have these optimizations. That's kind of like thinking like on one hand, I have these RDDs, which are low level. You can think of, for those of you who've played with different languages, such as C++ language, and then you have data frames. You could think of Java, which has got this memory management. So you have all these optimizations on top that manage and take a lot of that low-level stuff away from you. So you focus on the higher-level stuff being more productive, and you know that these optimizations produce higher-level, faster code, which underneath, all of them are converted to RDDs in the end. So data frames can be created from a variety of sources. You could be reading and writing from Hive tables using Hive context, which we'll cover briefly. You could be reading from JSON, JDBC, ORC, or Parquet files, and of course HDFS. There are external plugins. So Spark has an external page where it lists all external packages. For example, if you need to have a package that reads CSV files, that package is available to you as well. And the way, if you know what RDDs are and you have some code in RDD, but you've specified schema and would like to convert them to a data frame, all you do is say this RDD to data frame, and using that function will create you a data frame that then you can manipulate using that data frame and have some interesting processing at a higher level. There we go. So quick comparison, because you'll see this in the notebooks as well. There are two contexts. There's a SQL context and a Hive context. In general, all you will need is to use SQL context in most of your instances. But in the cases where you would like to interact with the Hive tables or bring ORC files or have access to Hive user-defined functions, then you would use the Hive context. And as you recall, SC stands for Spark context, and the way you would define SQL context is basically called on this method, SQL context using the Spark context, or in the case of Hive context, you read just Hive context over this Spark context. And essentially, Hive context is just a superset of the functionality that you would want with SQL context. So just to make it very simple, Hive context if you're interacting with Hive tables and everything else, SQL context pretty much for anything else if you're not interacting with Hive tables. But the Hive context has all the functionality of SQL context. So let's go over some Spark SQL examples. So again, we're going to focus on the higher level stuff. It's an introductory crash course. For those of you who would like to explore more, there's more examples on the RDDs, which is the lower level stuff. So it's slightly harder to get into on a first pass. So I've decided to let's focus on Spark SQL. So the data frames and doing the SQL queries. So we bring in data in that's already structured, that's already formatted, and this is going to be the higher level, so it's going to be easier for you to kind of understand what's going on. So say this is a Scala syntax. Well, the only thing about here that Scala base is declaring this value. But say you have this flights table that already has been defined, and you're using a SQL context to bring it into a data frame. In the data frame API, all you would do is say you want to query for three columns. Is you use data frame select, and you would specify the columns name, origin, destination, and departure delay. This, by the way, is a flights delay data set that's used throughout a lot of demos. There's actually a full-blown demo in one of the Zeppelin notebooks. So it's useful to play around with this data set so you can go and explore this farther on your own. So as you can see, all I'm doing here is specifying 3 different columns and then using show 5 to show the 5 top row entries for this specific table. So here's an example where we're doing filtering. So again, this is an API where we just add on. It's more like a pipe that you're creating. So now we're applying a filter. And with this $, we're specifying that for this departure delay column, everything that's greater than 15 minutes, show me the top row. So you can see in this column, everything that's been above 15 minutes has been returned. So now let's go over the same example, just like this one. What would it look like in the SQL world? So using this data frame that's got already this data from the flights table, I'm going to register a temporary table called flights. And it's going to register this table in memory. So now we have this access of all this information in memory, so it's really fast. And now for those of you who've used SQL before, all you have to do is go SQL context.sql and create a query. So now all you do is select origin, destination, departure delay from flights where departure delay is greater than 15 minutes and limit to 5. And we just click show, and it shows the same data it did over here. So the point of this is there's 2 ways of accessing data. If you're more comfortable with the data frame syntax, you would use the data frame syntax API. If you're more comfortable using SQL to create the same data, you would use SQL. And underneath, you have this catalyst optimizer, so the speed and execution will be exactly the same. So of course, again, let's go over this comparison. To summarize, RDDs are this lower level API. It gives you more control. You can cache things, you can perform Lambda type of manipulation, transformations. There's lots of existing code and users that publish code because this is where Spark has started, so all this code is already there. It provides, of course, compile type safety, but on the other hand, you have data frames, which is the higher level API. This is what we're going to be covering here. You have faster sorting, hashing, and serialization. Of course, because of the catalyst, you have more opportunities for automatic optimizations, and it provides lower memory pressure. So there's a lot of benefits to using this higher level APIs. To give you another comparison is, on top you have an RDD example, and on the bottom you have a data frame example, and all it's doing is finding the average age by development or by department. So as you can see, there's a lot more that would take in processing that same data with an RDD versus the equivalent data frame with the higher level API. Another thing, like I mentioned before, there's the speed up optimizations. As you can see, whether it's Python or Scala data frames, they're much faster than the RDDs that have been written in Python or Scala. Python generally trails in the speed and execution, primarily because it's got the additional overhead of being an interpreted language. So let's go briefly about Spark streaming. So Spark streaming, so on one hand, you have, say you have batch data that you bring in. So whether it's on a daily basis, on an hourly basis, you can then run these batch jobs to process data. But what happens if you have data that's coming in near real time? Then you would do something that's called Spark streaming. And Spark streaming allows you to process data as it's coming in. And conceptually, it's very similar to doing batch processing. So now that you know how to process batch jobs, all you have to do in Spark streaming is process some data in a similar manner, but these are micro batches. So it's near real time. It's not real time because it's not event-based, but it creates these micro batches, generally half a second and more, where you process the incoming data. And again, because it's based on RDDs underneath, it's scalable, it's got a high throughput, and it's fault tolerant. This is essentially how the data will look like. You have input or data stream coming in. You have the Spark streaming engine processing data. And as you can see, these are batches of input data, or micro batches. And then you have the results processed on each single micro batch that then you can have displayed on a dashboard as the data is changing every half a second. Or you could store the results to an external layer and then process these as well. If you would like to calculate rolling average, something for those of you coming from the finance world, there's also there are windowing methods that could process the data and take a look, back in time and have this windowing functionality. So let's go briefly over what Zeppelin or Apache Zeppelin and HTTP Sandbox are and what you get within that sandbox environment. So Zeppelin is essentially a notebook. It's very similar to Jupyter, but it has additional enhancements that allow you to write, for those of you who've played, for example, Jupyter or Python notebooks, you can write with multiple languages in the same notebook. So you have these interpreters and backends, and whether it's Scala, whether it's Python, whether it's R, all these different languages can be written in the same notebook. And what's really cool, you can pass in the variables between different paragraphs. So there's a concept of not only Spark context or SQL context, but there's also Zeppelin context. And with Zeppelin context, you can pass in the variables between the different notebooks. So say you have a data scientist that wrote some of his data in R and would like to pass it to someone who written some of the processing in Python. You can use Zeppelin context to pass that data around. On top of that, you have rich visualizations that are built in within the Zeppelin notebook, and you have a chance to explore those in the lab. This is essentially the architecture of Zeppelin server, if that interests you and would like to take a picture for later. But you have these interpreters that you can plug in, whether it's Spark or PySpark, Spark with Python or Spark SQL. They share the single Spark driver. And then the dependencies, if you use Spark before or using Spark Submit, you can specify dependencies in the very first and top paragraph before you execute anything, and it will bring all the external packages that you need in your development in that space. So this is just a quick example of how you would share the variables between the different paragraphs in the notebook itself. As you can see, here I specify a paragraph that's executing Spark and Scala, and I'm passing the variable and I'm getting it in another paragraph right underneath that's written in Python. So that's the additional power that you get from this 100% open source notebook. This is the new UI that's coming soon. As you can see, they've improved quite a bit. So I'm excited about that. So what is not included in Spark? So Spark is this powerful compute engine, but it's missing a few things, right? It's missing the cluster management system. Some call it, the cluster operating system, and it's missing a storage layer. So what you get in your sandbox is multiple things. One, of course, you get the Zeppelin that's already integrated, that's already pre-configured. You get Yarn, which is essentially a resource management, a cluster management operating system, and you get your HDFS, which is a distributed fault-tolerant storage. So you get all these things that are pre-configured, so this way you can quickly start and have everything in one space. So if you download the data, you have the data stored on that virtual machine, you can pull it up, and you can write all your Spark code, whether it's R, Python, or Scala, or even Java, and run it from the Zeppelin notebook in one interface, which is fantastic for data scientists. Another way of looking at it, what you can do with Yarn, for those of you who still don't know what Yarn is, you can run not only batch processing and interactive, but also real-time. So it's one way of getting all these different systems together. And again, this is what you get in the sandbox. So now you can use Spark for batch processing, for large processing, 24 hours or more, or real-time, such as Spark streaming jobs with streaming data that's coming in, and you want to visualize it in near real-time. So Spark on Yarn, this is another way of looking at it, but this is how it is actually scheduled underneath. I know there's one gentleman that had that question. This should explain exactly what's going on. And why HDFS? Again, because it's distributed storage, so it's fault tolerant. If one of the storage nodes fails, it can recover and replicate the data on that failure node. And this, of course, outside of that Spark core, there's other tools. By default, we've disabled most of these services via Ambari, which is a UI that that you can stop and start certain services. So this way, even though it's 8 gigabytes in memory, and some of you might be laughing, it's a lot, but this is some of the minimum. So it's an environment that's been that's been designed and been created for all these tutorials. So we basically focus like, what is the bare minimum that we would need so you guys can quickly start and get going with a lot of these cool labs without having to spin up a cluster, with still being able to run it locally on your machine or in Azure in an expensive way. So tech preview, HTTP 2.5, for those of you who've heard about the announcement. A few things coming up, security via Livy server and then a Kerberos cluster. So now you'll be able to log in and have your notebooks securely stored, and each user will have access only to their own notebooks. And you can view user sessions behind the scenes. So one thing before I get into the lab, for those of you who haven't heard already about the Hortonworks Community Connection, if you do have questions and issues with whether it's a sandbox, Spark, or some data science questions, I highly encourage you to visit the Hortonworks Community Connection. It's a bit like Stack Overflow, but creating for big data. We're on there. I'm getting pinged if there's any questions related to Spark. So if you're having issues, and we're looking at it and we're trying to answer as many questions as possible. And it's growing rapidly since its inception late last year. All right, so let's go into the lab itself. For those of you, most of you should have that URL. So let me show you exactly where this URL leads you. So this URL should lead you to this document. If you click the first link, you basically go to this brief description on learning Spark with Zeppelin. And all it does is, because we released these sandboxes on the USBs slightly before, just for production terms, not all the notebooks that I've developed later or updated are available right away. So what happens is, all I ask you here is to execute the script that you haven't already, and it will bring in the latest labs and the latest notebooks with all the most current updates into your space. And what you should see is essentially this list of notebooks over here. Sorry, I keep forgetting. Let me go full screen. Yeah. So once you bring all the data, you have multiple notebooks. And today we're going to be covering Lab 102, the Intro to Spark with Scala. So let me briefly and quickly go over this notebook, and then I'll go around, and if you have questions and issues, we'll try to solve them, and then I'll go again and more deeply, paragraph by paragraph, of what's actually going on. So if I go to this notebook, few things to start with. There's a lot of markdown that I've used to comment a lot of things. But then as you go to these notebooks, the first thing you should do, first thing you should see probably, is you should see all these interpreters. So when you remember when I mentioned all these different interpreters, all these interpreters are defined here. So first thing you will do is click the Save button to make sure that all these interpreters are saved. And then the first thing you will actually execute is all these dependencies. And it's very important that you execute this paragraph first before any other. As you can see, this one is marked as a paragraph with dependencies. And the reason for that is because it needs to bring in the external libraries that will be used later. So once this is brought in, then you can check your Spark version by either clicking the play button, or as you can see, there's a tip. You can also hit Shift-Enter to execute that paragraph. And you should get a result of having Spark 160 as the Spark that's on your sandbox at this moment. So then I go briefly over downloading the different data sets that will be used throughout the labs. Another thing to point out, we're using the shell over here. So basically shell commands to bring in data and manipulate data just as you would from your terminal. We're moving data sets to HDFS, some preview of the data, and then we're starting to do different things in Zeppelin. First thing by creating a data frame from the data sets. So I'll leave you this for now. I wanted to stop at this point because some people always have questions like, what is going on right here? So I've left 2-3 sections that ask you to fill in the code. So hopefully by the time that you get to this fill in section, you've played a little bit with the code, and now you'll try and hopefully struggle just a little bit to make it still fun with the code that should go here. Basically, I'll ask you to, find the taxi in, destination, some operations on the flight data. But if you do struggle and cannot find it, here's an answer. You just click the Show Output icon. Right now it's a closed notebook. Right now it's an open notebook. And all you have to do is you copy and paste this code right over here, and you should be good to go. So I'm making this slightly harder, so this way you can pause and try to figure things on your own. So again, let me make this clear. So part 1 is using data frames as the API. As you recall, that's one way of interacting with data. And once you're done with that, so using data frames to analyze the airline data set, there's a part 2 that basically does the same thing, but now using SQL queries. So like as you recall, we registered the temporary table. the flights table. And now we're using SQL queries instead of the data frame API to look at and analyze the underlying data. And for SQL queries, all you have to do is you specify %SQL in your paragraphs. So then there's quite a few different things. Definitely read the comments. The comments explain mostly what's going on, and of course the titles in each paragraph. And we go through a lot of these things. We save and load back from ORC file. We compare to make sure that these data sets are of the same sizes. We then save the table permanently. So say you've operated some data, you've made some transitions, you would like to persist that data to HDFS. We do this at this point. We then read it again just to show you the different steps that you would take. So basically, after going through this lab, you would have the basic tools at your disposal of going through going from the very beginning to the very end of a process where you would analyze some data, take a look, you would transform some data, use parallelized distributed computing to get the results, and then save them back. And then you could save it and distribute it across your organization with other data engineers or data scientists to take a look at this data. So that's the reason why I'm giving you all these different examples over here, and I hope that this will be very useful. Then you can take a look what happens when you drop a table, because it's a managed system at this point, so you can drop a table and see what tables are there, and that's that. So with that, I'm going to put up this slide again with the tiny URL if you haven't had a chance to copy it, and I'm going to walk around. If you have questions, I'll be there at your disposal. Let me double check what is the time. So we have over an hour and 20 minutes. We'll try to finish around 5 o'clock. But of course, there are other resources, so we can continue this conversation. All my information is within that notebook, so feel free to email me, or feel free to post, even if you would like to have a faster reply, questions on Hortonworks Community Connection, because then it's not just me, it's the community and a lot of the solution engineers internally at Hortonworks that will be looking at and trying to answer your questions. So that's the best way actually on how to get a lot of help very, very quickly. With that, I'm going to pause my microphones and I'll be available on the floor.